Welcome students for my lectures, and in the last lecture we have discussed about CSTR with bypassing. I mean, kind of what happens if the CSTR contains the bypass stream. So in the present lecture what we are going to discuss about what happens if the CSTR contains the dead volume. Okay, based on the tracer curve experiments, how people will come to a conclusion that how the this is what we have discussed in the last class. A small recap. Okay, this is how the CSTR with bypass stream. Okay, based on this nature of the curves, we have identified whether this particular CSTR is having the problem of bypassing or dead volume. Okay, because nature of the curves. Okay, compared to ideal curves, how the non-ideal curve of the tracer curve experiment should look like. Okay, now we are going to study the because we have done example, people have done some tracer curve experiments. Based on this tracer curve experiments, we have to find out what is the kind of non-ideality that is existing in this particular reactor. Let us assume there is a CSTR which contains a dead volume at the bottom. Dead volume at the bottom means it is away from the stirrer and it is at the corners of the bottom of the tank, where is though there is no movement of molecules as such we can able to see. If that is the case, this particular portion of the volume is not available for the reaction. Molecules will get trapped here, and molecules will be remain at a longer period of time in this particular dead zones. Mainly the CSTR behaving like a ideal CSTR only at the top portion of the volume, where is near to stirrer. So let us find out that how the people identified based on this nature of the curves whether this is having the dead volume or not. Imagine there is a certain flow is into the reactor. Suddenly you have injected some amount of tracer, and you have at the end you have detected the tracer. Based on this tracer you have identified the kind of curve natures. Okay, let us, before you go into this non-ideal, let us figure out what is the ideal CSTR. How the ideal CSTR look, ideal curves of the CSTR should look like. Based on this ideal curve, you compare the non-ideal curve to identify what kind of non-ideality existing in this particular reactor. Okay, let us say there is a tracer you have injected. You have got the tracer E of t residence time distribution curve and cumulative time distribution curve. And if this reactor behaves ideally, this is how the ideal E of t should look like. Tau is the volume by volumetric flow, which is space time of the reactor. That means the curve actually should start at 1 by tau on the y-axis and exponentially decreasing nature you should see. This is how the nature of the ideal reactor. Here also at time t the molecule starts coming at the beginning of the time, so the fraction of or tracer molecules will rise and will reach to the value of 1 at maximum. Here this is how the profiles of E of t and F of t should look like. Okay, now compare this profile with this profile. Imagine there is a CSTR which contains the dead volume. Okay, now you have to remove this to what is the space time of this particular reactor, which is nothing but volume which is not dead, okay, divided by volumetric flow rate. Here I have divided the total volume of the reactor into two. One is the dead volume, which is represented by Vd, and second is the volume that is actually in working condition. That means this is which is nothing by Vdr. Then what is the actual space time of the reactor, which is nothing but volume which is not dead, that is Vdr, divided by total volumetric flow rate that is entering into particular reactor. So this is how my space time should look like. If reactor is containing the dead volume, okay, only this particular volume is in operation, then how my graph should look like. Okay, let us compare with ideal graph. What if this is an ideal CSTR, where my graph should start at 1 by tau, which has been proven from this ideal CSTR curve. The graph should start at 1 by tau and slowly the decay should look like. Okay, but if the graph is above the ideal curve, why it will start above the ideal curve? Now the space time, okay, has been reduced. Okay, 1 by tau will be higher than 1 by tau dr will be higher than 1 by tau, because tau dr is smaller now. Why it is smaller? The volumetric flow rate is the same, but the effective volume has been decreased. In such cases, the space time will of the reactor which is having the dead volume will drastically reduce. If tau dr is less than this is tau, then 1 by tau dr will be greater than 1 by tau. That means if your graph starts the higher than the ideal point, that means indirectly it gives the indication that this reactor is containing the dead volume. Okay. Now but through the tracer curve experiments you can able to find out the non-ideality in this non-ideal reactor. So this is how the E of t graph looks like, and which one comes down faster. You can see the red one is the the ideal CSTR is the black one. Okay, CSTR curve with the dead volume is the red one. You can see red one decay faster than the black one. It's very simple. The one which starts at higher point will drastically reduce compared to the one starts at the lower point, because exponential relationship is there. The one which is having the higher value will decay faster. One which is having the lower value decays slower. Okay, this is how the nature of the curve should look like. Okay, when you compare with the red ones is for the ideal CSTR, and the black one, I mean, you can see here I have represented in the, okay, other colors I have changed, then don't worry. Okay, this is one the CSTR with dead volume should look like. Okay, it will be above the ideal curve. Okay, which is the above the ideal curve. Okay, because of the dead volume, that more molecules will come out, because now they have less time to spend in the reactor. If you have less time to spend in the reactor, it will exit faster. That is, fraction of molecules will exit faster compared to the ideal one. So fraction of molecules that exist faster means the non-ideal graph will lie above the ideal graph, because at every time more molecules are coming out from the non-ideal reactor compared to the ideal reactor. Okay, now how the E of t function should look like. See, now you can see E of t for the ideal curve is 1 by tau into e power minus t by tau. What happens to the non-ideal curve? It is simply, you should not represent with the tau, you should represent with the tau dr, which is the space time of this particular actual reactor which is having the dead volume. So 1 by tau dr into e power minus tau dr. Okay, so here the f of t function, for the ideal one is 1 minus e power minus tau t by tau, and for the non-ideal one 1 minus e power minus t by tau dr. This is what the difference between the ideal and non-ideal CSTR which is having the dead volume. Okay, so you can read through these statements. So whatever explained here, which one will start early and which one start at the lower point. So this is what they explained here in this particular equation. Let us find out. And there is another indication that there is a dead volume. One is through this one. Example, I have told you that one is through the this particular points you can able to identify whether the CSTR is having the dead volume or not. Second, if you have very long curve, okay, long tail curves, okay, dead volume. Example, if you have a dead volume which is having very long tail curve. Long tail curve means the tracer molecules which trapped inside this particular dead volume will get slowly released. Okay, if the tracer molecules, there are some of the tracer molecules which enter the dead volume were slowly released, there will be long tail you are going to see at the E of t. If that is also the case, you can indirectly identify there is a kind of dead volume that is trapped, that is there in the particular CSTR. So this is what is explained here. Sometimes your long tail indicates also that you can able to identify the reactor is having the dead volume. So let us find out the small problem. Find space time of the non-ideal CSTR with a 20% dead volume. How I got 20%? From the tracer curve experiments I can able to identify how much, because how I can able to identify dead volume or not. See, because these curves, starting point of these curves, I can able to identify tau dr. From the tau dr and tau information, I can somehow able to judge that how much percentage of dead volume is happening in the particular reactor. Okay, find space time. So find space time of the non-ideal reactor with the 20%, okay, dead volume. That means nu 0 is the volumetric flow rate in the reactor, V is the volume of the total volume of the reactor, and what is the space time of this particular non-ideal reactor we are supposed to find out given total volume information, and what is the volumetric flow rate which is given. Volumetric flow rate is 1 liter per minute, and let us, what is the dead volume? It is nothing, given 20%, okay, of the total volume, which is nothing but 20% means 0.2 into this total volume, which is 20% of this total volume is the dead volume, which is nothing but 0.2 into 5, which is 1 liter. Then how to find out volume, that is excluding the dead volume, which is 5 minus 1, which is 4. 4 is the actual volume of the reactor that is contributing to the reaction or for the conversions. And now I got the information of total volume, dead volume, VRD, volumetric flow rate. Through the information I can able to find out what is the space time of this particular non-ideal CSTR, which is nothing volume, that is actual volume, that is useful, divided by total volumetric flow rate, which is 4 minutes. Then compare, let us compare with the ideal. So imagine it's an ideal reactor. Then what is the space time? Space time, that is nothing but total volume divided by total volumetric flow rate. That is, total volume is 5 liter divided by total volumetric flow rate is 5 minutes. Therefore 1 by tau, I know tau and tau dr. I know 1 by tau is equal to 1 by 5, which is 0.2. 1 by tau dr, which is nothing but 1 by 4, which is 0.25. That means I can able to identify the on the I of t graph, which one at the top, which one at the bottom. Okay. And you can imagine, if your reactor is having the dead volume, the space time will drastically reduce. Compared to ideal, it is a 5 minutes. Because of the 20% of the total volume of the CSTR is a dead volume, the effective space time in the reactor will get reduced to 4 minutes. Okay, I hope now you understood the concept of CSTR, which is having the non-ideality of the dead volume. So this is the beauty of the tracer curve experiments, and thank you. Let us meet with the new lecture.